In 13.3, we're going to do a problem like 17 and 19. So consider the vector r of t is equal to t squared for the first component. Then we have sine t minus t cosine t for the y component. And then finally cosine t plus t sine t for the z component. And we're only considering when the parameter t is positive. Part A says find the unit tangent and unit normal vectors, which are denoted in vector notation big T of t and big N of t. Also, we need to find the curvature kappa. So one nice thing is you are given equations for these things in the way of a formula sheet or on your quiz or test right on the actual thing. And so for our unit tangent vector, we have that it's r prime over the magnitude of r prime. So now we have somewhere to start that we can go ahead and just do that based on the given. So we have our r prime of t, which is pretty easy. It turns out to take a derivative of this vector of the vector r. You just do it component by component. It is a derivative also with respect to t, so we just take like a regular derivative as we're used to. So the derivative of t squared with respect to t is simply 2t. And so we'll go down the line here. For the next component, the derivative of sine t is cosine t, and then we get minus. Here we have to be a bit careful and remember that we have a function of t times another function of t, cosine of t, and that we need to use the product rule in that context to find the derivative. So I'm going to put parentheses here and I'm going to have t times the derivative of cosine t, which is negative sine t, plus, and then I'm going to have cosine t, the original function for that, times the derivative of t, which is 1. So that's a product rule applied for that component, that term of that component. Next thing, derivative of cosine t is negative sine t, and then we're running into another product rule situation, and so we just do that. Oops, sorry about that. Screen got switched up, the touch screen. Okay, coming back here. So then we're going to have t cosine t plus sine t times 1, which I'll just leave off this time. So a bit of cleaning up here. Simplify this a bit. First component's good to go. Next one, notice distributing this negative is necessary. And then if we look ahead to the next step, we're going to have cosine of t, and then it'll be minus cosine of t. So we'll get 0 there, and then all that will remain is t sine t. Kind of a similar thing ends up happening here for the last component. Negative sine t plus sine t is 0, and then plus t cosine t is what remains. So kind of easy to lose track of what we're doing, but notice that we're just trying to find the numerator of that fraction and for big T. So mission accomplished on that one, but we still have to find the magnitude of this r prime. So obviously we have to do that second, and we can go ahead and do it now. So we'll do it as side work. Remember that the magnitude is just going to be each component squared added, take the square root. So we're going to have 4t squared plus t sine t squared, because it's multiplication we can bring in that square. So we'll have t squared sine squared plus t squared cosine. Alright. That can be simplified. Notice that you can pull out a t. We'll do that in a couple steps here. So first pull out the t squared, and then you have 4 plus sine squared plus cosine squared. So in this next step we'll pull out the t root, and then notice we can use a trig identity. Sine squared plus cosine squared is 1. So then we're going to have 4 plus 1, which is 5. So So that really boiled down quite a bit. Alright, so now we can plug this stuff in. To our unit tangent vector, big T. And so now what we'll have, copying down the vector 2t, t sine t, t cosine t, over just t times the square root of 5. That simplifies because notice you can pull a t out of the top, and that will cancel with the 1 in the denominator. So we like to do that. And then one last step is maybe just bringing in the square root of 5. Although, as long as it's simplified otherwise, you can leave it out. Alright. So one down, we got our big T. So that was the unit tangent vector. Now we're going to the unit normal vector, otherwise known as the principal unit normal vector, which is its full name. But we'll just call it big N for now, that's easier. And you are also given a formulation for that. So if you again would refer to a formula sheet or right on your quiz or test, you would see that this is how it's defined. And it's very similar to how the unit vector is defined. So anyway, not that you have to observe that, but now going back, we have our big T, and then we can find these things. Because it's not too much work here, we'll just do it in context here. So when we take the derivative of 2 over the square root of 5 with respect to t, the derivative constant is 0. So we're just going to have 0 there. Next thing. The division by square root of 5 is like multiplying by 1 over the square root of 5. So that's a constant multiple. And so that's just you do not need to use the product rule. That's a waste of time. You can do that, but it's overkill. So we're going to have 1 over the square root of 5 times the derivative of sine t, which is negative cosine t. So that's the derivative of that one. Next thing, we have kind of the same business going on. 1 over the square root of 5, derivative of cosine is negative sine. And I just realized I took my derivative wrong because I'm confused with integrals, like you guys probably will be at some point, or have been. So let me go back. So the derivative of sine t is just cosine t. I just thought I was taking an integral for some reason. Let's grab that, get rid of it. Sorry about that. Okay, the rest of this looks good. That's the top. Down low, magnitude of that. So remember, we square everything, add it, square it. So then what we'll have, 0 for the first part, cosine squared over 5 plus sine squared over 5 root. So next thing, I can bring out a 1/5 root. That's going to simplify with a 1/5, or not 1/5, 1 over the square root of 5. So that's one thing I noticed here to simplify. And what else do we got going on here? So then what is left behind here is, whoops, it doesn't matter what order I make it, but maybe be consistent here, cosine squared first, And then notice we got our friend the trig, classic trig identity, Pythagorean identity. And so what we get is just 0 for the first component, cosine t for the second component, negative sine t for the final component. And that is our result for the normal, unit normal vector. So we actually do have part B. Just go ahead and do that. Find the curvature, kappa. So kappa has quite a few different formulations. You're given 2 of them. One of them we didn't go over and we didn't care about. One of them, actually another one was our definition. So out of those 4, were provided in the book anyway, you're given 2, and those are the ones that are usually in some form that you can calculate with them. So the one that's going to make sense out of the 2 that would be given, and again you don't have to memorize those other ones, is the one that's pretty much all set to go based on what we have already. So what that would be is our big T's derivative, its magnitude, over the magnitude of the derivative r. So if you go back, you can see that what we had on the top see, right back here, so when we were working on this, we had what we have here, and I'm just going to write it in this format with a 1 over the square root of 5 factored out, because I'm feeling a little lazy. And either will do. That's the magnitude of that. And whoops, I just realized we had that in the denominator already. Okay, backtrack, it's actually even easier than that. So follow our work here, and notice that we actually boiled all that down to, if we didn't cancel, just 1 over the square root of 5, because it was times 1. Okay, good thing I noticed that sooner rather than later. Next thing, notice we did all this work up above for the magnitude of the derivative of r. And so what we have here is our t squared 5. Okay, so we're going to simplify this. And we'll have 1 over 5t. So that's the curvature. And we're done with that example.